Section: Introduction. In this section, we have seen significant progress in large language models, LLMs, leading to the development of vision language models, VLMs. These models show strong abilities in tasks like visual question answering, image captioning, and understanding world knowledge. Vision encoders, such as CLIP and EVA, focus on extracting compact visual semantic representations, followed by adaptable language models like Llama and Vicuña to handle vision-language connections and instructions. However, encoder-based VLMs face challenges such as dealing with images of different shapes, high computational burden, and uncertainties in matching capacities between vision and language models. We have questioned whether it is feasible to integrate perception and reasoning capabilities into a single architecture without the constraints of vision encoders. Our empirical findings reveal that building encoder-free VLMs from scratch is highly challenging due to slow convergence and performance gaps compared to encoder-based VLMs. The key issues in constructing encoder-free VLMs include the lack of high-quality image-text data and the need for visual recognition capabilities. To address these challenges, we have introduced EVE7B, an encoder-free VLM derived from Vicuña 7B. EVE7B is trained efficiently with high-resolution images of arbitrary aspect ratios and competes well with encoder-based VLMs on various benchmarks. This approach not only outperforms existing models but also paves the way for future research in VLMs. By focusing on decoder-only models like EVE, we aim to develop scalable and efficient strategies for multimodality models that require less training data and computational resources. Our work builds on the integration of LLMs and LVMs to create effective VLMs. Commercial VLMs like Claude 3 Volt series and Step 1 Volt have expanded their capabilities to include images, texts, and videos. Open-source VLMs like Blip series and LLAVA series have shown promising results by bridging the gap between LVMs and LLMs. The importance of image resolution and aspect ratio for visual perception has been recognized, but current vision encoders face challenges in handling different image shapes efficiently. In conclusion, our approach of developing encoder-free VLMs like EVE7B offers a transparent and practical solution to the limitations of encoder-based VLMs. By bypassing the constraints of vision encoders and focusing on decoder-only models, we aim to enhance the efficiency and performance of vision language models for various applications. Section Summary. In this section, we delve into the challenges and potential drawbacks of existing encoder-based vision language models, VLMs, such as issues with image resolution, deployment overhead, and model capacity alignment between vision and language models. We propose EVE7B, an encoder-free VLM that efficiently handles high-resolution images with arbitrary aspect ratios, outperforming encoder-based VLMs like Fuyu 8B. By integrating visual recognition capabilities directly into VLMs and leveraging pre-trained data alignment, EVE offers a transparent and practical approach for future VLM research, showcasing promising potential for scalable and efficient training strategies in multimodality models. Section: Encoder-Free Vision Language Model. In this section, we present an encoder-free vision language model, EVE, that aims to bridge the gap between encoder-based and encoder-free VLMs. Our model, EVE, is designed to process image inputs without relying on an image encoder, making it unique in its approach. While EVE can handle high-resolution images with different aspect ratios efficiently, it currently shows only average performance on vision language tasks and lacks transparency in training strategies and data sources. Our research direction focuses on enhancing EVE's capabilities by leveraging supervised instruction datasets. We have identified two key lessons. First, prioritizing vision language pre-alignment is crucial before scaling up pre-trained data. This step stabilizes the training process and facilitates the integration of visual and linguistic information. Second, enhancing image recognition through visual representation supervision and language alignment leads to stronger visual representations for various vision language tasks. The architecture of our proposed EVE model includes a decoder-only design initialized by Vicuña 7b to acquire linguistic knowledge and instruction following abilities. We introduce a lightweight patch embedding layer to efficiently encode image and text inputs into the network. Additionally, we incorporate a patch aligning layer to align patch features with pairwise features from a vision encoder and predict next word labels generated by encoder-based VLMs. The patch embedding layer, PEL, in EVE is designed to transmit images almost losslessly without using deep encoders. We utilize convolution and pooling layers to process image features and incorporate cross-attention layers to enhance feature representations. The patch aligning layer, PAL, facilitates fine-grained representations by aligning visual features with the vision encoder's output. The training procedure for EVE involves 3 stages: LLM-guided pre-training, generative pre-training, and supervised fine-tuning. In each stage, we use different datasets and loss functions to train EVE on image and text data, aiming to improve its vision language capabilities progressively. Overall, our approach with EVE aims to develop a powerful and flexible VLM that can surpass existing models and bridge the gap between encoder-based and encoder-free architectures. Section Summary. In this section, we introduce the concept of an encoder-free vision language model, VLM, called FuU-8B, which is a decoder-only network that processes images directly without relying on an image encoder. Despite its simplicity, FuU-8B shows average performance on vision language tasks and lacks transparency in training strategies and data sources. To address these limitations, we propose a new model architecture called EVE that leverages pre-alignment of vision and language modalities, patch embedding layers, and patch aligning layers to enhance visual perception and language understanding, ultimately achieving performance surpassing FuU-8B and matching encoder-based VLMs. Section: Training Settings. In this section, we trained EVE using 33 million publicly available samples from SA1B, Open Images, and LAION. We only kept samples with image resolutions higher than 448 by 448 pixels. The text data from LAION was simple and noisy, lacking complexity and having duplication issues. To get more diverse images, we used K-means clustering on image features from EvaClip, resulting in 50,000 clusters. We then selected 300 images closest to each cluster center, creating a subset of 15 million images from LAION. We also used EMU2 and LLAVA 1.5 to improve image descriptions and remove repetitive or incomplete text samples. For supervised fine-tuning, we used datasets like LLAVA Mix 665K for EVE 7B and a mix of other datasets for a high-resolution version. EVE 7B was developed from Vicuña 7b for vision language tasks. We controlled complexity by limiting the longest image edge to 672 for EVE 7B and 1344 for EVE 7B, HD. We used clip VIT-L14 as the visual encoder and followed specific protocols for image resizing and padding. The optimization process involved using the AtomW optimizer, warm-up strategy, and cosine scheduler. The learning rates and batch sizes varied across training stages. When evaluating EVE, we found it outperformed FuU-8B in various benchmarks despite its smaller size. The incorporation of diverse datasets and larger images in EVE HD improved its image recognition abilities significantly. EVE HD also showed competitive performance compared to encoder-based models without needing additional visual encoders for complex image encoding. However, EVE faced challenges in specific instructions and language competency due to extensive training with only vision language data. Despite this, EVE 7B performed relatively well compared to encoder-based models, showcasing the potential of encoder-free models with proper training strategies and high-quality data. Section Summary. In this section, we detail the training settings and data preparation for EVE. We utilize diverse pre-training datasets like SA1B, Open Images, and LAION, curating a subset of 15M high-quality image samples. For supervised fine-tuning, we incorporate datasets like AI2D and SynthDog, enhancing Eve's image recognition capabilities. Despite facing challenges in specific instruction responses, Eve demonstrates competitive performance against encoder-based VLMs, showcasing the potential of encoder-free models with appropriate training strategies and high-quality data. Section: Ablation Studies. In this section, we explore different configurations of patch embedding and aligning layers through ablation studies to validate the effectiveness of our proposed PEL and PAL. We conducted experiments with various models trained using different datasets and training stages. We observed that removing any cross-attention layer in PEL led to a slight decrease in performance. Pairwise patch alignments performed better than next patch prediction, especially when using visual supervision via PAL, which enhanced fine-grained image representations and accelerated model convergence. During Stage 1, the LLM-guided pre-aligning stage played a crucial role in efficient training by stabilizing the process and preventing sudden collapses. This stage facilitated a smooth transition into Stage 2, emphasizing its importance in constructing an encoder-free VLM. Increasing image resolutions and incorporating diverse instruction data in Stage 3 resulted in significant performance gains after achieving a well-aligned state across modalities in Stages 1 to 2. Merging patch features across layers outperformed using only the last layer output, as shown in our findings. Optimal performance was achieved when selecting cross-layer features with an interval factor of 4 in PAL. This multi-layer aggregation approach proved superior to relying solely on the last layer output, as it enabled adaptive alignments with abundant characteristics from the vision encoder. Eve consistently improved with more pre-training data, nearing the performance of encoder-based models. By optimizing flops and minimizing inference latency, Eve ensured rapid and efficient processing, making encoder-free VLMs more practical and efficient than encoder-based VLMs in real-world applications. Section Summary. In this section, we conducted ablation studies on different configurations of patch embedding and aligning layers to validate the effectiveness of our proposed PEL and PAL models. We observed that removing any cross-attention layer in PEL led to a slight performance decrease. Pairwise patch alignments performed better than next patch prediction, and visual supervision via PAL enhanced fine-grained image representations, aiding in model convergence. Additionally, our training strategies, including pre-aligning between vision and language in Stage 1, stabilizes the training process, prevents collapses, and expedites convergence, ultimately leading to efficient training of an encoder-free VLM with improved visual recognition capabilities. Section: Limitation and Discussion. In this section, we present our limitations and discussions. We have developed Eve, which features an encoder-free decoder-only architecture that addresses various issues seen in encoder-based VLMs. However, a notable limitation is that there is still a performance gap between Eve and the top encoder-based VLMs. Moreover, due to time constraints, we have some unanswered questions and considerations. Firstly, we have observed that training solely with vision language data can lead to a decrease in language capability while enhancing multimodal performance. This suggests a forgetting of linguistic knowledge within the LLM. To tackle this, we propose merging language and multimodal data appropriately or using mixture of experts (MO) strategies to reduce vision-language interference. Secondly, we are exploring the potential of encoder-free VLMs to compete with encoder-based VLMs when provided with larger training samples. We are investigating how these models would perform under the same LLM capacity and training data. We hypothesize that increasing the LLM capacity and training data could enable encoder-free VLMs to match or even surpass encoder-based VLMs, benefiting from the direct image inputs that bypass preprocessing by vision encoders. Lastly, we are inspired to integrate additional modalities such as audio, video, thermal, and depth. The idea is to align these modalities with a frozen LLM from an LLM-centric perspective before introducing comprehensive unified training. This training would be supervised by corresponding single-modality encoders and linguistic conceptual alignments.